Welcome back to Applied Mathematics. In this video, I want to talk about solving linear inequalities. The process of solving a linear inequality is very similar to solving a linear equation, but having the inequality, having some of the behavior there, opens up a few new possibilities. Let me get my head out of the way and let's go through the basic idea. One of the key differences between a linear equation and a linear inequality is that every linear inequality has infinitely many solutions. So if I have x is greater than 3, I can sketch out a number line, locate 3 on the number line, maybe provide a little bit more information, putting 2 and 4, right, the previous number and the next number. X is greater than 3 means we're talking about the things this way, continuing on indefinitely. There's a couple of different notations for indicating the stopping point. I tend to use an open bracket, which looks like a parenthesis, which comes up to but doesn't quite hit 3 itself on the number line. Some sources will put an open circle there, right? A circle at 3, but not filled in to indicate that 3 itself is not part of the solution. Either of those are perfectly acceptable. They can be used interchangeably. There's some particular reasons that one or the other might be more useful in a particular application, none of which are going to come up in this course. Contrast that with x is greater than or equal to 3. Which is essentially the same, but in this case, 3 itself wants to be one of the values. To indicate that 3 itself is included, I like using a square bracket, which solidly hits the number 3. Again, the other notation that's common is a filled-in circle. That is also perfectly valid, but the square bracket and the, we call it a closed bracket, and the open bracket generally go together. And then to complete the set, we can also have x is less than 3 or x is less than or equal to 3. The rules for solving inequalities work the same as the rules for solving equations, except for one caveat. If I can write, one caveat on the multiplication property. The multiplication property says that if c is greater than 0, if c is a positive number, then no matter which inequality symbol you use, I'm using less than or equal here just for convenience, but all 4 of the inequality symbols work the same way. If a is less than or equal to b, then a times c is less than or equal to b times c. But if c is less than 0, if c is a negative number, and a is less than or equal to b, then a times c will be greater than or equal to b times c. To understand why that's the case, let's think about some particular numbers. How about 3 is less than or equal to 7? I think everyone will agree that 3 is less than or equal to 7. If I multiply both sides of this inequality by positive 2, I will get that 6 is less than or equal to 14, which again, absolutely true. If I multiply both sides of the inequality by -2, then I will get -6 and -14. Right? Thinking about the way a number line works, very much not drawn to scale, but -6 is further to the right, -14 is further to the left. -6 is greater than -14. So there's a very clear example. Multiplying by a negative number changes the direction of the inequality symbol. Other than that, the process of solving an inequality is the same as the process of solving an equation. So if I have something like 7 minus x over 5 is less than or equal to 9. All right, this is kind of a nasty equation from the beginning. There's a lot going on here. Following the order of operations, we would subtract 7 minus x first and then divide by 5. So, to solve, we have to get rid of divide by 5 first, which means multiply by 5. 9 times 5 is 45. Now I have 7 minus x. This is another place that things are a little bit messy. The 7 here is positive, so to get rid of it, we are going to subtract 7 from both sides of the inequality. And 45 minus 7 is 38. Finally, to get x by itself, we have the opposite of x. We've seen in other applications, in other circumstances, we can think of the opposite of x as -1 times x, which makes it a little bit more clear that to get x by itself, we're going to divide by -1. And because we moved this -1 from the left side of the inequality to the right side, we change the direction of the inequality symbol, and the solution here is that x is greater than or equal to -38. Right. When I'm solving inequalities, I will almost always graph my solution because, again, there are infinitely many solutions, and making sure that it's clear 38 is not the only solution. Oops, I'm talking and writing at the same time. That's not going so well. But we can just fill in a couple more values. We had 38, -39, -37 are nearby. We have greater than or equal, which means that we want that square bracket that solidly hits -38. And then we fill in the greater direction, which is over that way. All right. One of the other things that is really nice about inequalities is that we can start to talk about things as three-piece inequalities. A three-piece inequality, instead of having one inequality symbol, is going to have two. Consider here, -5 is less than or equal to 2x plus 3 is less than or equal to 27. Consider here, -5 is less than or equal to 2x plus 3 is less than 27. Notice here that I have a different inequality symbol. I have less than or equal to on this one, I have strictly less than on that one. You are allowed to mix and match, but it always has to be these two. right? Less than is allowed, less than or equal to is allowed. For reasons of aesthetics, you are not allowed to use greater than or equal to in a three-piece inequality. It always has to be less than or equal to. Other than that, it's the same process. It's a little bit weird because instead of having two sides of an equation to do things on, we have three sides of a three-piece inequality, but we still have this x in the middle and we want to figure it out, so we'll subtract 3 from all three sides of the inequality, which gives me negative 8 is less than or equal to 2x is less than 24. And then I will get x by itself by dividing by 2, which gives me negative 4 is less than or equal to x is less than 12. All right. To get some sense of what's going on here, I can sketch out a number line. The only two values I really care about are negative 4 and positive 12, but if you want to fill in a little bit more, you're welcome to. I am not the kind of stickler that says fill in every value, but equally spaced is nice. So if I count by fours, negative 4, 0, 8, oh, I can't count by fours apparently. Negative 4, 0, 4, 8, 12. We'll just pretend that those are equally spaced. We could keep going over here and get 16. We could keep going over here and get negative 8. I'm not that worried about those sorts of things. I just want to get the basic idea in place. All right. X is between negative 4 and 12. Between is the stuff in here. On the negative 4 side, we have less than or equal. That means that 4 itself is a solution to the inequality. I'll indicate that using the square bracket. On the 12 side, we have strictly less than. That means that 12 is not a solution to the inequality. I'll indicate that using the parenthesis. Three-piece inequalities are useful in a number of applications. The one that might be most important for our course is they are another way of discussing a tolerance. We've used the significant digits shorthand for this entire course, and we will continue to use the significant digits approximation for the rest of the course, but three-piece inequalities do allow us another option that gives a little bit more precision. All right. The usual significant digits approximation, or the significant digits approach, tells us that if we have a measurement like 12.7 centimeters. And let's just go ahead and give that thing a label. We measured that x is 12.7 centimeters. The interpretation that we have used is that that means that x is somewhere between 12.6 and 12.8. And we're kind of stuck with whole number values, or whole step values on whatever place we are. Sometimes that's useful, and sometimes it's not. So, let's imagine that we have a precise measuring tool, but it doesn't measure in the 10th of a centimeter or the 100th of a centimeter. It measures to the nearest 5 micrometers, or I guess it would be 50 micrometers. So maybe it turns out that x is somewhere between 12.685 and 12. 690. All right, that's a different level of precision than the significant digits approximation can give us. I don't want to spend a lot of time thinking about this because it's not what we are going to use, but it's one of the important reasons that we talk about inequalities, because it gives you the language for talking about precision like this in an application that needs it. All right, for our purposes though, I think I'm going to wrap up with that. So thank you as always for joining me. I'll see you next time.